Welcome to every flavor of robot. Wow. Y'all ever see a Rover do that? That's great. We were freaking out whenever we got the Rover to do this. We've had some fun these past couple of weeks, testing our motor controllers, playing around with the Rover, breaking stuff, writing bugs, the usual. Oh, and we launched a Kickstarter for our new motor control board, so you should check that out. But here's a question for y'all. What happens when you make a new robot design, cram it into another robot, design and make all the parts for it, and film it and edit it in 1 week? I don't know. We didn't get that far. But it sure wasn't for a lack of effort, and I think that we learned a thing or two that's worth sharing on the old YouTube channel. So, let's get to it. We made this jumping test stand to see how much power we could pump through the board just in one quick moment. I'm working on fully characterizing, all of the specs on this board and our motor system, but for now I just wanted to make something that was fun and I could use it to do a static torque test later. I just put an arm on a rail, so if the arm hit the ground, then it would push the board up the rollers. So the rollers are what's keeping it on the rail, but I was a little worried because I'm not using like the traditional material for them that you would buy online. I'm just 3D printing them. And PLA doesn't have a lot of friction, but turned out fine. So, moving on. Didn't want to take off the board for the Rover or the other projects we have, so I'm building up a new one. This is the encoder connector. And then just started programming it to move between two positions while it was on my desk before we moved it over to some test stands. Now we were able to make it jump off the ground and catch itself. At peak power, it was drawing about 120 watts into one motor. I would love to hold the board at constant power and see how long it takes to burn, but the power supply was just giving up. And then the board falls to the ground, and we're just gonna have to solve that later, because we're moving on to the steering. But before we move on to the steering, we have to talk about this video's sponsor, PCBWAY. I've said it before, I'll say it again. You need to know about PCBWAY if you're looking for PCB prototyping or assemblies, or they even do 3D printing, CNCing, and a bunch of other stuff. Go check out their website and see what they can help you with. I really do think they do a good job. This is the board that they sent us. It looks pretty clean, and more importantly, here is the one that they sent us fully assembled. Very nice. And thank you again to PCBWAY for sponsoring every flavor robot. We were talking about the steering. Right now the Rover implements what we call skid steering, which means that at the center of its turn, if you want to make a turn, you're going to have to make some of the wheels slip and slide on the ground. You can see that happening right here. Since you need your wheels to slip, you can't drive that well, and that is proverbially not the move. So we have to fix that. A balance spot doesn't have problems turning on the spot though, which is why we started asking ourselves, can we make the Rover balance? Turns out the answer is yes. It's not the best balance spot ever, but it's not the best Rover ever either, and this was more of a proof of concept. I think it more than shows it's good enough. Heck. Yeah. Heck. 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 So then Swapnil and I got to talking. We're like, well, let's just combine the two. And if we design it really well and work really hard and get a little lucky, we'll probably end up with the worst of both worlds, if I had to guess. But we're going to try it anyway. So I started designing a combination of the two robots. And I wanted to go over my drawings, but I don't really know what I was doing.
Like, what the heck happened here? I only draw two teeth on my rack gear. This one also was, these are supposed to be like little, I don't even remember what I was trying to draw with this.
Just imagine two motors that can drive up and down these rails, and at the bottom of the rails are the wheels. And if we make those racks strong enough that they can hold the robot up, and we're gonna hold them in place with more rollers, just like the jumping rail test stand. And then you can just use your imagination to figure out how the rest of it works, but it kind of ends up looking something like this. And boy oh boy, did I try to assemble this robot this week. And man, I ran out of time. It started with just like, a couple parts needing a little edit here and there, and then quickly devolved into just utter chaos. I mean, I was following no design guidelines anymore. If you look at this Onshape document, had like close to 80 extrudes and parts and features and stuff. I mean, it truly just had gotten a bit out of hand, and it was only getting messier and messier, and so I decided I needed to take a step away and just accept that this time the goal was too ambitious. And there's still a part of me that's sad that I couldn't be Iron Man and create all of this in one go in my garage, but I'm making these videos to show you what we're doing. And sometimes what we do doesn't work. What are you gonna do about it? Let's look at the bright side. A lot of the parts turned out well. One big win is that this is the first time we've ever had all three 3D printers working at the same time. So that's where the hardware of the robot is, but the software has been going through something really exciting. Swapnil has been translating it from what we had working before, which was in simulation, to the real world. And I just want to go over a couple of terms with y'all so that everyone understands what's going on, and a couple of broad concepts before we dive into the details. So we're going to go over here and we're going to talk about the simulated environment versus the real environment. First off, I wanted to bring this up because it's something I was always curious about, but it took me a long time to get over this like oh my god, simulation's so crazy, that's wild. And thankfully I was surrounded by like really smart people like Swapnil who helped me understand what's going on, and that it's not that complicated. And I think by the end of this, you're going to definitely understand what's happening in our project with simulation, but you'll actually be able to understand like how simulation is just used in robotics in general. So first off, like, why are we simulating stuff? Well, anytime you design something, one of the first principles of engineering is to isolate your problem, divide and conquer. If you're trying to make a perfect steak and potatoes dinner, it's way easier to cook them in separate pans and put them together at the end than it is to toss everything in the same pot and hope that you can micromanage everything. Often, simulation environments just lets us test our big code, like planning where to go or what to do, without worrying about super tiny details like, oh, are the wheels going to do what we ask them to do, or like resetting and recharging the batteries every time you want to run a test. So that's why you'd want to simulate. But what counts as simulation? Honestly, like, I define it as anytime you're replacing a real world input or output with a stand-in. And that could look like a virtual sensor that your robot code can ask, hey, how far am I from the ground? It doesn't have to be virtual though. You could simulate forces that a rocket launch would put on your project with a centrifuge, or vice versa, though I don't think anyone has ever done that. But let's talk about the very specifics of our project, because I think that's the easiest way to explain this. We have a robot code, the brains of the operation, and the inputs that we gave it were completely simulated. We used a program called Gazebo, and it's very common in robotics, and its inputs and outputs were all going through this environment that the robot fakely existed in. The outputs of the code affected the Gazebo space by telling Gazebo that we move the robot around, which then affects what Gazebo tells us our sensors are reading. So it's a real loop, but it's just not in the real world. And if we want to move it to the real world, all we have to do is line up the inputs and outputs. In our project, we have 3 inputs, and we have basically just 1 output. The output command is where to go. Do we go forward, left, right? We turn. The inputs are all measurements of the world, whether that's a virtual world or a real world, doesn't matter to the robot brain. So let's talk about, say, the encoders, which tell us how far our wheels have traveled. So what does that look like in simulation? Hey, Gazebo encoders, how far have you turned? And they're like, like 5 times. And we're like, okay, 5 times. So now in real life, it's super easy. We just say, not Gazebo encoders, but hey, real encoders, how far have you turned? And they're like, 5 times. And the rest of the code's the same. And that's all it takes to transfer it into the real world. So I hope some of that made sense, and now we're gonna see Swapnil do that, but in real life.
All right, so we're trying to read out the data from the wheels here. The data is really choppy for some reason. I don't know why. Let's figure out what's going on. Okay, I think the choppiness is my fault. The velocity is updating, and the position is incrementing. I think we're okay now. I think it's working. Next step is seeing if our measurement of our position is correct. I'm gonna drive the robot forward, and you can see that's not correct. So we're taking encoder data from the encoders on the wheels now, hidden back here. And we're doing some math. The wheel encoders give us a pretty good estimate of where the robot is. When you're going over a really short distance, it's pretty accurate. The wheels only give you bad estimates over really long distances. As I drive the robot around, our measurement of where the robot is on the map seems to be changing. That's Is that about a meter? It says it's about a meter. What is this? Some of our math is slightly wrong because it's saying that we've driven a meter. The other cool thing is it handles the rotation. So if I rotate the robot, it shows that it's rotating, and that is actually scaled correctly. That is going 90 degrees. So that's step one. We need to get this robot working like the simulator did earlier in the last video. The simulator was giving us 3 things. It was simulating what the motors would do. Obviously, we don't need to do any simulation for that in the real world. But based on that, the simulation gives you back how much the wheels have spun, right? Like their estimated change in position from the simulator. So step one is computing where our robot is moving based on our wheel position. Step two is doing the same thing with the LiDAR. So we need to get the LiDAR data into the simulator, and then we need to do the same thing for the IMU. We need to read the IMU data. So basically the wheel encoder data, the LiDAR data, and the IMU data. And once we have those 3, we should be able to plug in all the same autonomy stack, and it should work. So we got our IMU guy right here, wired up to our Raspberry Pi. LiDAR is on right now too. So we have the IMU coming in, and then so we read the gyro data, we read the accelerometer and the magnetometer, and from that we figure out the orientation of the robot. So you can see we'll twist, or we'll pick up first, and we'll rotate, pick it up, rotate 45 degrees, back. You can kind of see that all of its behavior is being picked up by this coordinate frame, and then when we return it returns back to the same position. So the IMU data is good. That's what I like to see. You can see here the LiDAR is doing like a 2D sweep of everything around my room, and basically it's sending out a bunch of little laser points, sending out a bunch of little lasers to measure the distance to a bunch of points. So you can see this corner right here. And in the simulation, you'll see the corner there. I'm waving my hand, you can see my hand going back and forth. So all these little tiny dots on the display are the little tiny laser measurements. So what's cool about all of this now is the LiDAR points, if we've done all of our math correctly, should never move relative to the coordinate grid below it. You can see when I grab the robot and drive it back and forth, the LiDAR data pretty much stays in the same place where the robot is moving. I think this is clear when I rotate it. You'll see that the robot is rotating, but the LiDAR data points for the most part are staying the same. There's a little bit of drift, which is coming from me letting the wheels slip a little bit, and also picking up the robot. The LiDAR is slightly scanning some different points and all. But for the most part, you see that it's working as expected.
If you made it this far, seriously, please consider checking out our Kickstarter. It is in the description of this video, and it closes in just 4 days. We're trying to get this open source motor controller off the ground and into as many people's hands as possible because we think it can help people build better robots. Consider giving us a subscribe and a like if you liked the video, and let us know what you think in the comments. Thanks for watching.